currently being returned to. This scheme is very efficient for well leveling, but it requires expensive full merge operations, as shown in the bottom figure, where many pages are moved and copied. To avoid CPU processing and passing around large pages through the channel multiplexer demultiplexer, we perform in hardware this expensive merge operation during garbage collection inside each low-level controller. To protect against failures happening due to radiation of the space environment, we propose many fault tolerance features. As discussed before, we have a network of cubes, and we can use redundant array of independent disks, RAID technique, in order to rebuild failed modules. We also propose a specific metadata layout. Inside, we store information necessary to rebuild the FTL logical block map and related data structure as startup. It is also used to store else metrics such as program erase cycles. The address metadata is used by the controller to validate page reads and the address translation table. The timestamp inside the metadata is useful for scrubbing validation and identification, and the data hash serves as additional verification of boot data. To validate our concept, we have 3 levels of validation. To test the correct functioning of the FTL firmware, we develop a custom C++ trace-driven emulator of the flash controller, along with NAND stack and MRAM caching. You can see on the top right figure that while executing the trace, we can observe the status of each die in the stack using a monitoring GUI. Secondly, we implement the microprocessor on ARM Cortex-M3 along with the RTL accelerator using an FPGA. We verify that the RTL controller works well by using simulation with non-Verilog Micron models. To conclude, our loaf-of-bread stacking method allows the heterogeneous integration of COTS devices of NAND flash and MRAM dies into the same cube structure. Our NAND flash cube is supplemented with a SSD logic controller architecture, integrating many new fault tolerance features. We believe that our old memory package allows new space missions, which were not possible with the current memory devices. We developed our cube in an open architecture for design flexibility. Indeed, we developed the controller and the cube in parallel, so that we can interchange the NAND flash dies, for example, in case of technology roadmap changes or unsatisfactory radiation results. Thank you.
Well, thank you so much. We don't have that much time, but if there is any question for the speaker, please type your question in the chat box. No question? Well, I have one question for you, and very briefly, if you can answer it, I appreciate it. Is that what are the trade-offs of the implementation? How is the controller tested for radiation immunity? Can you quickly answer that?
Hi, hello. So for radiation, because we haven't finished the full implementation of the controller in ASIC, we mainly tested by simulating some faults in RTL and to see if the RTL could take charge of errors happening logic-wise. If we're talking about ASIC implementation, compared to the original design, we will use many more RTL-based fault tolerance feature like duplication. So more important parts will be duplicated, and there will be some kind of voting to improve the fault tolerance. And obviously, we will use a technology that will be radiation hardened, and most likely a more older technology, maybe 130 nanometers, which are known to be more radiation hardened. And obviously, once the full controller has been built, there will be real radar tests under proton radiation.
Thank you so much. I have to
Thank you.
stop it here. I appreciate the
Okay.
answer.
Thank you. Thank you,
Very
everyone.
much. Thank you. That was a very good
Thanks.
presentation. So our second presenter is, and I apologize if I pronounce it wrongly. Please correct me. Ankit Weigel. He is a PhD student at Arizona State University, and his paper would be a configurable BNN ASIC using a network programmable threshold logic standard cells. I'm gonna share my screen and we will listen to his presentation.
Hi, my name is Ankit Wagle. I am a PhD student at Arizona State University. I am here today to present a novel architecture for accelerating BNNs using a network of programmable threshold logic standard cells. I would like to thank NSF PFI for supporting this project. In a gist, this presentation will demonstrate how a highly efficient BNN accelerator is built using threshold logic cells or neuron cells. We will show that it is possible to achieve a 3x improvement in energy efficiency over an existing state-of-the-art architecture without sacrificing area, performance, or even accuracy. It should be noted that these improvements were achieved without using any of the standard low-power techniques such as voltage scaling or approximate computing. Before we deep dive into the architecture, it is necessary to understand what threshold functions are. Threshold functions are a subset of Boolean functions which are linearly separable. They are represented using the equation shown in this slide. As you can see, we first calculate the weighted sum of inputs. If this sum is greater than the threshold t, then the output is 1. Otherwise, it's 0. These functions can be easily implemented using the hardware neuron shown in this slide. There are 4 main components: the left and the right input network, the sense amplifier, and the latch. The left and the right input networks calculate the weighted sum and the threshold in the form of currents. The sense amplifier compares these currents from left and right input networks and performs the evaluation of the threshold function at the rising edge of the clock. Finally, the latch stores the result of the threshold function. In simplified terms, a neuron is equivalent to a flip-flop with embedded logic functionality. Note that a neuron is built using flash transistors, which are CMOS compatible. We will now show how a processing element is constructed. It's constructed using 4 neurons connected to each other. We call this processing element a tulip P. Each neuron is also connected to a local register from which data can be accessed or written to. Using this arrangement, it is possible to implement several operations used in the BNNs, such as addition, comparison, batch normalization, max pooling, and ReLU. Although the details on how these operations are performed on the tulip P can be found in the paper, we will show the flow used for executing these operations in the next slide. The nodes in a BNN are large threshold functions with typically 1,000 inputs or more. The flow shown on the slide helps to execute these BNN nodes on a tulip P. First, each node is decomposed into a network of smaller threshold functions. Then, with appropriate inputs available to the Ps, these threshold functions are scheduled on the neurons. All the intermediate data generated within the network are stored on the local registers. Finally, the result of the tulip P is extracted through the output buffers. Now that we know how a BNN node is executed on a Tulip P, we can now look at how the top-level architecture operates. We built a single instruction multiple data architecture using the Tulip Ps. The L1 and L2 image buffers are used to cache and broadcast image data to the Ps. The kernel buffer provides the weights to the Ps. We also have memory and processing unit controllers to help operate the architecture. We have additional MAC units within the architecture for handling layers with integer activations. Now, in order to evaluate this architecture, we chose another benchmark architecture by the name of YodaNN. This architecture was chosen as it evaluates BNNs without using voltage scaling or approximate computing. We constructed both the YodaNN architecture and the Tulip architecture using TSMC 40 nanometer LP process. Both the architectures were evaluated by performing a 288 input neuron computation. It was seen that the Tulip P consumes about 60 times lower power as compared to the MAC unit. However, it is also 25 times slower than a MAC unit. Still, on the whole, the Tulip P has about 2.3x better energy delay product, while being 23 times smaller than the MAC unit. Although the processing elements show promising results, it is necessary to evaluate the top-level architecture to gauge the final benefits of using the Tulip P. We perform the evaluation using two neural networks. First is the binary net for CFAR10 image classification, and second is the AlexNet for ImageNet image classification. This table shows the comparison between YodaNN and Tulip architecture for convolution layers. It can be seen that the energy of Tulip is 3 times less than the energy required by YodaNN. Since the performance of both the architectures is about the same, the energy efficiency also improves by 3x. Then we extended this experiment to see how the two architectures perform when fully connected layers are included in the evaluation. When fully connected layers are implemented on both the architectures, most of the cycles and power is taken by the memory instead of the processing elements. Due to this, there is no difference between the energy and performance between the Tulip and YodaNN during the fully connected layers. Hence, the overall improvements in energy efficiency and even energy dilute from 3x to about 2.4x. Through this presentation, we showed that the Tulip architecture delivers better energy efficiency than the state-of-the-art architecture. This work can be further extended in multiple directions. First, we need to explore additional arrangements for the Tulip P that can help improve performance. Then we need to see how the improvements can be boosted using voltage scaling and approximate computing. We should also explore alternate memory architectures that are used for data distribution of image and the kernels. Finally, we should explore various loop unrolling strategies that are used to improve the performance. Thank you.
Well, thank you so much. Any question for our speaker? So then, if there is no question, I'm gonna ask a very brief question. I appreciate a brief answer because we don't have that much time. But I really enjoyed the presentation. So, how are the flash cells programmed in the neurons? Can you please comment on that?
So generally flash transistors are floating gate transistors, so they require high voltage 20 volt signals to program them once. These voltages are generally broadcasted. And then once you program them initially at the time of manufacturing, you don't need to program them later on. Yeah.
Okay. Interesting. Well, thank you so much. Any other question for our speaker? If not, we would move
Thank
to...
you.
Sure, of course. Thank you. That was a very good presentation. I enjoy your work. So our third speaker is and please sometimes correct me if I pronounce the name, I mispronounce the name, is Raikda El Shabhabi. She is basically a PhD candidate in University of Vienna, TU Vienna in Vienna, and she will present us her work on the effects of permanent faults in QDI circuits, a quantitative perspective. I'm going to share my screen and we will all listen to her presentation.
My name is Rada Ekşeh. My name is Rada Ekşehevi and I'm a PhD candidate at the Technical University of Vienna. I would like to present to you our work on the effects of permanent faults in QDI circuits, a quantitative perspective. In contrast to synchronous systems, the operation of asynchronous circuits is driven by a causal chain of events using some kind of handshake between any two entities. In a quasi-delay-insensitive system, delay-insensitive codes are used for communication to indicate when a new data word is ready to be captured by the receiver, which in turn sends back an acknowledged signal to the sender. The indication principle requires each transition issued by the sender to be acknowledged by the receiver, making this type of communication very robust against timing variations. Our work focuses on permanent faults where the circuit simply stops operating in the absence of transitions needed to trigger further activity. To represent permanent faults, we chose the stuck-at-fault model, where a signal can become permanently stuck either at logic high, namely stuck at 1, or at logic low, stuck at 0. According to literature, a stuck-at-fault in a delay-insensitive circuit can either be inhibiting, preventing a transition from taking place, or stimulating, causing a transition to occur prematurely. This figure visualizes our analysis and shows how an inhibiting fault would cause the circuit to keep its correct state while being detected immediately or later. A stimulating fault, on the other hand, might pollute the circuit's internal state before deadlock. As we can see, all possible effects eventually lead to the circuit deadlocking, the only difference being the state in which the circuit resides before stopping operation. The benign path highlighted in the figure represents the compelling fail-stop behavior that we would like to maximize after exploring the relative occurrence rate of the different effects of a stuck-at-fault in a QDI circuit. Our experiments aim to provide a quantitative analysis of the circuit's behavior. To this end, our investigation is conducted through fault injection experiments on the shown target circuit in the figure. The circuit is composed of a 3-stage pipeline with the middle stage as a victim where we inject single stuck-at-faults. The logic function is a half-adder with a 2-bit data path implemented in the delay-insensitive midterm synthesis method following the dual-rail 4-phase communication protocol. Our latch uses 2 completion detectors with a Muller-C gate deciding when to capture new data. As previously mentioned, our experiments involve injecting faults into a VHDL model of our system, which is executed in Mentor Graphics Model Sim HDL simulator. We injected faults into our victim stage, taking into account fault polarity, injecting both stuck-at-0 and stuck-at-1 faults, fault location, injecting in all inputs and outputs of the gates of the target stage, varying the speed of source indicating when new data is ready, and that of sync to note when old data has been consumed. And finally, we make sure to hit all possible time intervals where a fault might have an effect. For our analysis, we identify the following possible effects: immediate freeze, where the pipeline freezes without moving to a subsequent phase, late detection, where some tokens keep moving forward in the pipeline before the circuit comes to a halt, and premature fire, where the fault causes a transition to occur before it is scheduled. We monitored and classified the behavior of our system under test by comparing it to a second, identical but fault-free pipeline as a golden reference. Our results show the relative occurrence rate of the three different effects with respect to varying the delays of sink and source. As we can see, late detection is the dominant effect, ranging from about 65 to 93% as the sink becomes faster, which we refer to as a token-limited mode of operation. Immediate freeze and premature fire occur much less, both increasing as the source becomes faster than the sink, namely bubble-limited mode. Our next experiment attempted to quantify how many cases, with respect to the different effects, resulted in polluting the state of the circuit before resulting in deadlock. Overall, we observed a proportion of 13 to 30% of faults to corrupt the pipeline state relative to the speed of source and sink. The proportion of incorrect behavior with respect to each effect is further broken down. Finally, I would like to conclude with a summary of our work and some notes on our future work. We have provided a quantitative investigation of the effects of permanent faults in QDI circuits through fault injection simulations. Our results confirm that a QDI circuit always deadlocks in the presence of permanent faults. We have observed three different effects: immediate freeze, late detection being the dominant effect, and premature fire. We have also observed a non-negligible proportion of 13 to 30% of faults causing state corruption. Our future work will extend the analysis to more complex target circuits as well as other pipeline styles and protocols. Thank you.
Well, thank you so much. That was an excellent presentation, nice and concise. Any question for our speaker? Oh, we have one question from Martin S. Interesting topic. Is there an intention plan to implement this into a silicon?
Yes, in the long run that would be in our plan. We currently are still at the first stages of actually quantifying to getting numbers in order to actually build a prototype and then move on maybe to silicon.
Very good. That would be exciting, I guess.
Yeah.
Any other question for a speaker? Well, thank you so much. Then we will move to the next presentation. I'm just checking the chat box. No, we don't have any other question. So our next speaker is Ross Thompson. He's pursuing his PhD in Electrical Engineering Department, Oklahoma State University, and his presentation would be on a novel rounding algorithm for high performance IEEE 745 double precision floating point multiplier. I'm gonna share my screen and we all listen to this presentation.
My name is
from the top.
Hello, my name is Ross Thompson. Today I'll be presenting a novel rounding algorithm for IEEE 754 floating point multiplication. This work is done with my PhD advisor, Dr. James Stein. Our paper is titled A Novel Rounding Algorithm for a High Performance IEEE 754 Double Precision Floating Point Multiplier. To begin, we will have a short review on floating point multiplication, and then we will move on to a classic rounding algorithm known as injection rounding. And then we will introduce our new rounding methodology called dual injection rounding. Then we will briefly talk about the implementation methodology and the verification and results. So what exactly is floating point? So floating point is an IEEE 754 standard, which is used to approximate real numbers over finite range and precision. The standard defines various sizes, such as single and double precision, and then additionally the operations you might want to apply to our numbers, such as addition, subtraction, and multiplication. Floating point numbers consist of 3 fields, a sign, an exponent, and mantissa. And their values are expressed in 2 different equations. The first is the normal representation represented by equation 1, and the second is the denormal representation in equation 2. So the floating point algorithm is relatively straightforward, at least initially. You XOR the sign bits together, add the exponents, and then use unsigned multiplication for the mantissas. The things start to get a little more complicated once we realize that we have to round our numbers, and additionally, may have to normalize the product. What exactly does that mean? Well, IEEE numbers require that the mantissa lie in the range of 1 to 2. Unfortunately, multiplication can end up producing results that lie outside this range, specifically in the range of 2 to 4. So for example, if we multiply the number 3 times 3, if we write them out in their floating point binary representation, and we look like we have 1.1 times 1.1. When we multiply that together, we get 10.01. And unfortunately, this is greater than 2. So that means we have to shift our number over and add 1 to the exponent. There's also another issue, which is the operand or the product could be denormal, and that requires additional complications to the algorithm. So if we want to look at the basic block diagram of what a multiplier looks like, it starts with a circuit to unpack the mantissa, which is just discovering what the value of the hidden bit is. And then we end up multiplying the mantissas together using a partial product reduction tree. And then in parallel, the exponents get computed. And then based off of whether or not the inputs and the output may or may not be denormal, there's a shifter which adjusts the position of the mantissa. And then finally, we do the final addition, rounding, and overflow. And this presentation and paper focus on the rounding and overflow. Injection rounding. So one method of rounding a floating point number is to add a small constant, slightly smaller than the unit in the last place, such that when you truncate the bits that aren't going to be part of the final result, you end up implementing a different rounding algorithm other than truncation. So to do this, injection rounding ends up building this constant called injection no overflow, which adds it to the intermediate product. The problem is that this method only works if you don't overflow your result. So in our example of 3 times 3, this isn't going to work. Fortunately, there's a workaround for this. The algorithm describes how you can add a second correction constant through this somewhat complicated algorithm by splitting the data path into 2 sections, and I'll briefly describe that in a moment. The other issue is that the injection constant actually doesn't implement round to nearest even. Instead, it implements round to nearest up, and there's a conversion process for that. So this block diagram shows the lower half of the multiplier, where you're feeding in your carry safe format from the partial product reduction tree, and you're adding in your injection constant. And what you'll notice is that the upper half is just 52 bits, and it's going to produce a sum of the carry save plus the injection constant, or plus 1. And the lower half is going to be the part that decides whether or not we actually increment the result or not. So in contrast, our method directly adds the injection constant just as in the single injection constant version. But rather than do this correction business, instead we add a separate injection constant for the overflow condition. And you can see that the value of the constants is slightly larger. So then we end up producing 2 separate sums, which is in contrast to how the single injection constant works. And then we end up using the MSB of the no overflow sum to select between the 2 for our final product. So my apologies, this diagram is quite large and busy, but it has to split over multiple slides. This slide shows the upper portions of the multiplier. The first part is the unpacking component, which finds the hidden bit, and then we've got the partial product reduction tree and the exponent calculation, and finally the shifters required to do the denormalization. Additionally, the overflow data path is shown in orange rather than black. This slide continues what we just saw, and in it at the top we have the injection constant addition. So you can see there's two different injection constants being added, but importantly, there's only two bits that are different between the two, so we can leverage a lot of redundancy between those two. Additionally, the carry propagate adder, there's a lot of commonality between the inputs. There's a lot of common factors, so we can factor those out. And finally, we have this little section down here, which is responsible for doing that conversion from round to nearest up to round to nearest even. So what does our optimized adder look like? Well, first of all, we did a lot of experimentation to find the optimal architecture for the adder for this multiplier. We found that to be a Koge stone with a sparsity of 8. So the parallel prefix tree has partial duplication of some of the black cells that are part of the adder, and those are shown in red. So the red cells are the ones that are computing the overflow, and the black cells are the ones computing the no overflow. This is just a zoomed in version of that. You can see that there really aren't that many additional cells added to the design, despite the fact that we have two separate sums. So we need to verify the functionality of this design, and we do that using test float and in addition of several other test vectors. And then we also need to verify the non-functional performance of the design, so delay, area, and power. And we do that by implementing our designs in GlobalFoundries 14 nanometer low process power technology using standard cells. And we go through a fairly typical synthesis and place and route paradigm. Our results are the timing, extracted timing parasitics of the final sign-off from Innovis. And then finally, we need to generate really accurate power numbers, and we do this by using vector-driven power analysis. So what do our results look like? Well, our design is not only faster, but it also uses less area and less energy compared to the standard single injection version. Importantly, a figure of merit, the power delay product, is significantly better for our proposed dual injector. It's also important to consider how the design performs across multiple different target speeds. So while it's true that our new dual injector algorithm is faster than the single injector algorithm, we also might want to consider how the performance changes or how much energy we need if we target a slower clock speed. And that's what this graph is showing here. On the x-axis we have delay, and on the y-axis we have dynamic power. You can see in green is the dual injector, and in purple is the single injector. Similarly, the area is better for all targets for the dual injector. So in conclusion, we've been able to develop a new rounding algorithm which is not only faster, but uses less energy and is a smaller total area. That power and area advantage is maintained across different target clock speeds. And finally, the way in which we achieve this higher performance is by factoring out a significant amount of the two 161-bit adders. Future improvements may also be possible if we consider how we might optimize the denormal shifting. Thank you, and that concludes my presentation.
Well, thank you so much. Your results are quite impressive. So any question for a speaker? So I'm going to ask a short question. I appreciate a brief response. So what other adder architectures did you consider for the carry propagate adder?
Yes, so we considered many of the different types of parallel prefix trees. Specifically, we looked at Koge stone, ladder, Fisher, and Skalansky. We also varied the sparsity from no sparsity all the way up to sparsity of 8.
Well, thank you so much. I appreciate the brief response. So we will move to the next presentation with the title of An Implementation of External Capacityless Low Dropout Voltage Regulator in 45 nanometer technology with output voltage ranging from 0.4 watt to 1.2 0.4 volt to 1.2 volts. It is a pretty lengthy title. So our speaker is Farid Ahmed, who's a fourth-year PhD student at University of Missouri, Kansas City. I'm gonna share my screen and we will listen to his talk.
Hello, everyone.
One second.
Hello, everyone. Today I am presenting our work, which is accepted for short paper in ICCD 2020. Our work is on an implementation of external capacitorless low dropout voltage regulator in 45 nanometer technology with output voltage ranging from 0.4 volt to 1.2 volt. Here I am Farid Ahmed, one of the authors of this work. This is the overview of our presentation. First, we'll tell about the contribution of this work, then the overview of the proposed design, some key simulation results, then the comparison with the prior works. So in this paper, we make the following contributions. Proposed a fully on-chip LDO in 45 nanometer technology, where no external capacitor is needed. We introduced an additional loop by replacing the resistive feedback network to get the overall improved performance. Like the transient performance, we're trying to achieve good transient performance and as well as the PSRR. Designed the LDO with a very small activity and wide output range. And we investigated the issue of LDO in lower node and addressed them because like there are very few designs are available currently in 45 nanometer. And at the end, we are comparing the proposed design with the state of the art prior works. So this is the overview of our design. If you see the A, block diagram of A, that's the traditional LDO. And B, that is our proposed LDO. We replace the resistive feedback network with the in-mode pass transistor. And there is an additional loop you can see. And the third figure is the schematic diagram of error amplifier, the common source stage, and the buffer. So basically, like the error amplifier is, so if you look at the figure B, there are like 4 or 5 components here. One is the error amplifier. Second is common source stage there, and the buffer. And we have 2 pass transistors instead of 1, which is different from the traditional design. So the error amplifier basically a differential amplifier having one input as input reference voltage and other input coming from the output node as a feedback. And the output of the EA is going to the common source stage, and the other input for the common source is coming from the reference voltage. The output of this common source is fed to NMOS transistor, NMOS pass transistor, and this cascaded structure of error amplifier and the common source stage is creating a 2-pole system. So for stability, we used one 10 picofarad compensator capacitor, and the output of EA also goes to buffer, and from buffer to the PMOS. So by controlling these 2 pass transistors, we are actually achieving the output voltage. Pass transistors are chosen with large sizing value to provide enough current to the load. Depending on the reference voltage, output voltage is regulated by controlling the gate voltage of the 2 pass transistors. Here you can see the simulation results. First one is the it's reference voltage tracking actually. So whenever we are switching the transient analysis, when we are switching the reference voltage, the output of the LDO is following actually properly. The second one is the load transient performance. We are giving a step input into load from 0 to 12 milliampere current, and if, as you see, it is like quite good achieving the output voltage at 1.2. There are some spikes here and there, but other than that, we are getting the 1.2. The third one is for different load voltage. We are showing that we are achieving different, like a wide range of output voltage from 0.4 to 1.2 actually. The fourth the figure here, you can see the line regulation curve, and for this line regulation, we are actually, the input operating range here is 1.8 volt to 2.8 volt, and we got the line regulation as 2.6. This is the output volt versus load current curve. For different load current, we are showing that we are getting a stable output voltage for all in this range load current. And the last figure here is showing the PSRR. So we are achieving around 31 dB PSRR. And if you see, there are two regions here. One is for LDO, like one is covering by the LDO active area, and other, like the second region, those are like coming from the Cout, the output capacitor. This is the comparison with the prior work. In this work, we are simulated in 45 nanometer technology. There are actually few designs available now in literature. So we compared with like all the available designs, like in 65, 45, and 40, near like whatever we found in the literature. As you see here, the output voltage, there is variable. We are getting 0.4 to 1.2 volts. The voltage drop is higher here, like 600 millivolt. We're trying to like improve this parameter in our next design. And the quiescent current is quite low than the other design, like 7.82 microampere. The active area is also low than all other compared to all other designs. If you look at the like on-chip capacitor, we need only like 10. No output capacitor is needed. So like the whole design is fully on chip. If you look at the line and road regulation, our value is much better than all the other designs here. The PSRR is like a little bit okay. Like we were trying, like in our next design, we're trying to improve our PSRR. That's all for today. Like if you have a question, please ask me. Here are the references we used for like for our work. Thank you.
Well, thank you for the presentation. Any question for our speaker? So I asked a question and I appreciate a brief response. So what are the major limitations of your proposed approach?
So like one of the thing I already explained in the presentation, like the transient response, the spikes, those are not good for the design. So we are trying to improve that. Other thing is PSR. So yeah, so in our present design, like the PSR much improved, like almost twice the updated design. And other thing is like if I go for the fabrication of this design, so I have to go a deep NL process, because in the second pass transistor, the body is connected to the source, and which is not ground. So for fabrication, I have to go different process. So that is a complication.
Okay, makes sense. Well, thank you for the response. So we move to the next presentation, which is the last presentation of this session. Our presenter is Professor Shiyu Huang, who is currently a professor at National Tsinghua University in Taiwan. So he will present for us his paper on duty cycle correction for a clock signal supporting a super wide frequency range from 10 megahertz to 1.2 gigahertz. Seems very interesting presentation. Looking forward to it. I'm going to share my screen.
Hello.
Let me.
My name is.
Bring the video. And
Hello, my name is Xu Huang. I'm from National Tsinghua University. I'm going to present a paper entitled Duty Cycle Correction for Super Wide Frequency Range from 10 MHz to 1.2 GHz. So the duty cycle of a clock signal is the fraction of one clock period during which the clock signal is active. In this work, a clock signal is active when it is high. So given a clock signal like this, duty cycle is around 33%. We want to convert it into 50% duty cycle. Prior works on duty cycle corrector design mostly use open loop structure. So the drawback is they are mostly susceptible to PVT and aging effects. So we want to make two improvements. First of all, we want to create a design that's more accurate using the closed loop structure. So it will be truly process and temperature resilient. Secondly, we want to create the even wider frequency range duty cycle correction design to support a frequency range from 10 MHz to 1.2 GHz. And so we will be able to support aggressive dynamic voltage and frequency scaling. So the foundation of this work is a duty cycle monitor that we have developed previously, which is highly accurate. For example, this duty cycle monitor will be able to answer a query such as, is the high phase amount or low phase amount of a given clock signal larger, within the accuracy of a few picoseconds. This is the architecture of proposed closed-loop duty cycle corrector. It consists of 5 major components: flip-flop here, half-period tunable delay line here, one-shot circuit here, duty cycle monitor we mentioned here, and the controller. The idea is this flip-flop operates in the sequence of trigger and wait for a half period and then reset type of operations. Its input is skew clock like this. The output is Sierra KOUT. And then basically the skew clock will delay by exactly half period before triggering the one-shot signal, making the whole design behaving like a duty cycle corrector. And the key is this duty cycle monitor has to be highly accurate to guide the search process of this half period tunable delay line to make it highly accurate as well. So this is the layout of our design when incorporated together with wide frequency range delay line loop supporting 10 MHz to 1.2 GHz. The upper part is the duty cycle monitor, and the area inside the yellow boundary is the wide range delay line loop. Here is the simulation waveforms when we switch the frequency of the input clock signal from 1.2 GHz to 100 MHz. The DLL will be relocked first, and the DCC will be relocked again. After both are locked again, then we can check the output clock signal is exactly very close to 50% duty cycle. Also, the output clock signal is not exactly in phase with the input clock signal. This is the table showing the locking time and the duty cycle errors of our design for various input clock frequency from 10 MHz to 1.2 GHz. As you can see, the results are all very accurate, close to 50% duty cycle, with the errors within around 1% or less than 1%. In conclusion, previous duty cycle correctors are susceptible to PVT and aging effects. And so in this work, we incorporate a highly accurate duty cycle monitor to guide our correction process to make our duty cycle corrector more resilient to PVD and aging effects while supporting a wide frequency range. This concludes my presentation. Thank you.
Well, thank you so much. That was very interesting presentation. Any question for a speaker?
My husband's administration has worked to try and
Let me see the chat room. Any question for a speaker? Well, I have one question, and then after that we will conclude this session. So why is your DCC design more temperature resilient? Can you please elaborate on that?
Yes, because it incorporates a closed loop structure. So constantly, we will check the output clock signal and to make sure that it's always 50% in terms of its duty cycle. So even the temperature change, this closed loop will continue tracking. So the duty cycle will not introduce any error in that.
So your voice was breaking. Can you please repeat the last part?
Yeah, so when the temperature changes, we react through this closed loop feedback structure. So we can adjust to that. Especially, usually the temperature will not change very rapidly. So I think dealing with the temperature variation shouldn't be a problem.
Okay, that makes sense. Interesting. Well, thank you so much. I appreciate all the speakers for their good presentation and answering the questions, as well as all attendees for attending this session. So we will conclude this session almost on time. We will have a 30 minutes break before the next session. Have a good one, everyone. Bye-bye.
Bye-bye. Thank you.
Thank you. Thank you, everyone.
Thank you, Hamid. So I'm going to stop the recording and I'll be prepared for the next session. Thank you so much.
I recorded on the cloud. I hope it is fine, right? That's the.
I did record it to the cloud. That's okay.
Thank you. Have a good one.
Thank you.